to download this file that you see here. Let me just share screen. So we're looking at this set of notes now, the conservation equations. So up to now, we've been talking about solving the balances. So our differential equations, we had derived them for each description. And in each particular geometry, we derived the material balance and so on. And now we're starting to see solutions to those equations when we implement the boundary conditions and all that. And we will continue with that type of work. So we are going to look at more case studies and more examples and more solutions. But for what we'll do today, we are going to try to generalize our development of these, of the material balances and also other types of balances. So you see the way that we are currently doing it, we describe a situation, we define the boundary conditions, and we define our finite volume and so on. And in a way, it's rather it can be rather specific. It means that we have to apply a great deal of intellectual effort just to be able to develop the equations for the systems that we describe. At the same time, we've been seeing a number of persistent patterns. We see diffusion terms, and quite often those diffusion terms have a second order expression in the final equation. We know there's a convection term sometimes. So we feel that there might be an underlying governing, if you like, description of the physics of the problem. So there's some underlying description. And if we couldn't get to that, then we can get away from the complication of, oh, here on this surface is 2 pi r delta z, and on that surface it's 2 pi r delta r, and all of that. So all of that is quite specific to the geometry that we've been looking at. Whereas what we could look for is some way of describing our systems which doesn't actually depend on the geometry, right? We don't have to sit there and scratch our heads, oh, this is rectangular, oh no, this was cylindrical, oh wait, now this one is spherical, and we get totally different expressions every time, and it feels like a whole other set of theory. So we would like to unify all our attempts to develop these material balances, and we have to generalize our geometry then. And the surprising thing is that the best way to do this is by going back to the very fundamentals of calculus. And in fact, the fundamental theorem of calculus, right? How much more fundamental can you get? So the fundamental theorem of calculus is the basis of what we'll do. So just reflecting on the purpose of this course, chemical engineering fundamentals. What we want to show today is that it's actually based on the fundamentals of calculus. So the fundamentals of chemical engineering are no different to the fundamentals of calculus. And towards that, you might recall the fundamental theorem of calculus, which states this. So if we have some function, y of x, and so you can see some arbitrary y function shown here, plotted y on the y-axis and x on the x-axis. Then if we pick 2 points, x2 and x1, then we can say the difference between these two values, right? Looking at this value and this value, the difference between those two is equal to the integral that we get when we add up all the contributions from the gradients in between, right? That's a way to look at what we're saying here. Another way to look at it is through, if you like, let's think of 1 second. Let me just get the right thing here. Another way to think of it is just in terms of the definition of a derivative. Okay, just sharing screen again. So let's look at the definition of a derivative. So we know we've got dy dx is equal to some function. And in this case, we'll just say it's a function of x. Let's not worry about differential equations or anything like that. Then we know that if we integrate this, right, so if we take the integral of this function, so the integral of dy dx, oops, integral. I'm so looking forward to Monday when we can just write on the board again. So the integral of dy dx, and we are integrating with respect to x, right? And if you look at this, you can see effectively it's going to be y, the difference in y values, right? If you want to write in the limits of this integration, we are integrating from x1 to x2. So this is basically the integral of dy. So if we look at this, this is nothing but the integral of dy. The integral of dy, which we can write as y2 minus y1. Okay, so that's very consistent with our definition of a derivative, right? So from our definition of a derivative, we can practically immediately see the fundamental theorem of calculus. So here's our theorem of calculus. And again, if you look at this equation, you can see that what it's actually saying is this difference between these values, y1 and y2, of course, we can just look them up as we've done here and subtract these two numbers. So that's one way to get this. But it's saying here, the other way to get it is if you take the derivative at each point along the line and you integrate all those derivatives, then you'll end up with the same difference. So number one, looking at this difference, by the end of the day, we have a function here and we can identify any 2 points and we can subtract them and say, that's the distance. Or we can use the fundamental theorem and we can add up all these. And of course, it seems like an unnecessarily complicated way to do it, right? Why would you want to go and do it that way? Why would you want to integrate all these derivatives when you could simply subtract the values like this? But we'll see having this available opens many doors for us. So I just want to check, is everybody on the same page, right? The fundamental theorem of calculus, you're all familiar with that, and that looks like what you remember from your Maths 1 class. Okay, thank you. And so if that's the fundamental theorem of calculus, we are going to generalize that. So if you like, this version of the fundamental theorem of calculus is in effect a line integral. So this is a line. So in a one-dimensional space, we have this curve and we are integrating around this curve. In, of course, a three-dimensional world, we would need to extend this. And we have available to us the divergence theorem. Have you met the divergence theorem as yet? It seems not, right? So let's just look at it. So you will derive it fully in your maths class, but let's just look at the meaning of this. So the divergence theorem tells us that if you have some vector field F, so for instance, imagine that imagine a fluid, and we've got a velocity vector field in that fluid. So if you pick any point in that fluid, you can find a vector that tells you this is the direction in which the fluid is flowing at that point. And if you were to integrate what's happening on the surface of the space, so we are picking a space here. There is a certain volume, not a finite volume, an actual volume. So there's some, I mean, not a differentially small volume or something like that. And there's some actual volume. And of course, that volume has a boundary, and on that boundary, we identify an area. So just imagine in three-dimensional space, some kind of lump, right? And an irregularly spaced lump. And so we've got an area of this three-dimensional surface. And if we look at the surface and we look at the vector field values on the surface of that space, and we add up, if we integrate this all around that surface, then we'll get a certain number, right? By the end of the day, when you integrate all this on the surface, you'll get some number. And you will get the same number if, instead of integrating only on the surface, you integrate all the interior points in this space. So you've got some lump. You can imagine a grid, a three-dimensional grid, right? So in your lump, there are a bunch of X, Y, Z positions we can identify. So if we add up the so-called divergence of the same field across the volume, then we'll get the same number that we'll get if we integrate on the surface. The only unknown here is this div, right? What is the divergence? So the divergence is defined, it's defined as the derivative in all directions. I'm just skipping ahead to that. So here we go. So the divergence of a vector field is equal to the derivative of a vector field with respect to each spatial dimension. So it's in effect a derivative of a field, right? It's a high dimensional version of differentiating a high dimensional function. So once more, the vector field F, that gives us a vector at each point in our space. And so we can identify a component of the vector in the X direction, in the Y direction, and in the Z direction. All of this applies at every point in the space. So when we say these are the components of a vector, this is of a specific vector sitting at some point in the space. And as we look at different points in the space, we get different values of this vector. And that vector is changing. So if you compare that vector to its neighbor, right, just next to the vector at some distance delta x, there's a different vector, and so that vector has changed to some extent. Similarly in y, when we look at the neighbor in the y direction, so if you imagine your house, you've got a neighbor across the road, so maybe if across the road is the y direction, then you've got a neighbor on the same side of the road, you've got one on this side and one on that side, so you've got derivatives in the different directions. You've got neighbors in different directions, and so we can look at the rate of change of some value. So between you and your neighbor, maybe if you look at I don't know, the height of your roof, like your neighbor has a different height to you. So if you compare the height of your roof and the height of your neighbor across the road's roof, there'll be some gradient there. And if you look at the height of your roof compared with your neighbor on the same side of the road, that will be a different derivative. So that's what these all mean. So this divergence is the sum of all these derivatives, right? So that's your divergence. And what we're saying here is we can, inside our space, we can evaluate the divergence at each point, and we can add up, we can integrate over the whole volume, and that will give us some number. So we get a number here by adding up the changes inside the space, and that will turn out to be equal to what we get if we integrate on the surface only. So that's the divergence theorem. And if you compare it with the fundamental theorem of calculus, it's actually the same thing, right? If you look at this line integral, right, your interior points are all these x values between x1 and x2, and you can regard x1 and x2 as the surface positions, right? So your actual space is between these 2 points, but the edges of that space, right, it's a one-dimensional space. So at the edges, you've got x1 and x2. So the difference on the edges, this is basically what we get by adding up the changes at the ends here. And that is equivalent to adding up the changes on the surface in the three-dimensional case. And like we said in the theorem of calculus, we can integrate through the volume. So here we are integrating all the changes along the line here. In a similar way, we are integrating all the derivatives at the interior of the space. So we can imagine all the derivatives inside of the space here. And here, in a similar way, when we look at interior points, there are derivatives. So whenever you look at the divergence theorem and it looks a bit unfamiliar, it's useful to go back to the fundamental theorem of calculus, which is usually expressed in the one-dimensional case. And you can look for this kind of analogy. But, any questions or comments on that? And let's now look at, just moving the chat box here. So let's now look at a kind of instance of this in our, in rectangular coordinates, right? So it's a little bit easier to see when we look at it in rectangular coordinates. So let's imagine that we have this box as our space. So here we have a three-dimensional box, and we can see the dimensions. So in the x direction, the box starts at position x and ends at position b. And then in the y direction, you can see we start at c and end at d. And in z, it's from e to f, right? So that's our box. And that what we just said is expressed there as well. And now we are interested in some velocity vector field. So for instance, there might be a fluid, and this box is an imaginary space sitting inside of that fluid. So let F be some field that we're interested in, like a velocity vector field, right? Now, we can imagine the changes in the flux across that box. And let's for now just look in the x direction. So we're saying we want to know what's the change across this box. So let's look at what's entering the box. So entering the box is arriving on this face, right? If we can specify this face here, you can see this edge CD, and then moving along this edge here, which is DF. So that's the edge DF, and this is the edge. This is DF, and here, this is D. It's not DF also. This is so that's E. Yeah, that's point E. So if we're talking about Z, that is F, and then that's the. So here, in terms of the height, so this face basically. So here, where you see a slightly lighter velocity, you can see that's the face that we are fluxing into, right? So the line CD and then D to this point, which is at the point where we have FD, and then from here down to this point where the value is C. So this is the point CF. This is the point DF. So this face here. So the flux into this face, that's so the flux at that point, and we can call that area A1. So we are fluxing into this area A1, right, which is at CD. What is this? This is at not E. Yeah, this is at F, and so CD, and here this point DF. So that face. So that's the face CD and EF. That's what's coming in, and then coming out here, we are at a different x position. So here the x position is a B. So coming out on this face, you can see the B here, and then it's the same. The surface area is the same on this face. Your value of the field is different. We are looking at a different x position. Here it's the x position A, that's the x position B. So we are fluxing into and out of this space. And we're not as yet applying the divergence theorem. We're not as yet looking at integrating anything. We're just saying that's flux in and flux out. And we can see that these integrals are the same, right? We've got integrals in y and z. and we've got the same limits, right? C to D and E to F, C to D and E to F, because the only thing that has changed is X. So we've got the flux in and out of the space. And so we can group these two together and we can say it's one difference where only the X values are different there. So that's just the difference in terms of what's happening in the area. And then if we look at our fundamental theorem of calculus, we are saying here that that difference must equal the change of the field in the X direction. So if we compute the derivative of the X component of the field, right? If we compute that derivative and we add up all those changes in the X direction, then that number must be the same as that difference. And so we can then say that applies at some specific, right? That's looking at the line integral in X, and that applies to all positions. If we don't just want this difference at a specific point, right? This difference here is evaluated at some position Y and some position Z. So if we pick on this surface, right? Imagine, oops, sorry, there's a bit of a lag here. Yeah. So if we can imagine picking some Y and Z, remember there's Y changing in this direction and Z changing this way. So if we pick a Y and Z, then that fixes a point here and it fixes a point there. So this is just a point difference, but we don't want a point difference. We want a whole volume difference. So we are looking for the integral of the flux across the whole area. And we have to do it this way because the flux may be changing from point to point. If we imagine some real volume here, and we've got different velocities at different points on this face, then we won't be able to represent this as one flux. So instead, we acknowledge that the flux is different for the different positions on this area. And so we have to integrate over the area to get the net flux. And I guess there's supposed to be a minus sign here, by the way, right? So just that correction is needed. But anyway, so there's a flux difference here. And if we are integrating this over the area, then we also have to integrate this in the area. So integrating in Y and Z here gives us this. And if we look at this, this is nothing but the flux difference. So we can rewrite it like this, right? So we can say that the integral through the volume, so this is now looking at it in the X direction. So just acknowledging that this right-hand side is nothing but the volume integral of df dx, right? Then that difference across the area is equal to that. So that's what we got for the X direction. And then we get that also for, we can do the same exercise for the Y and Z axes, right? So we also get that. And by the way, I know I said just now it's supposed to be a minus sign, but actually when I think about it, what we've shown here is that it's the area. So this area, even though we think of area as a scalar, right? If you think of area, it's just some distance times some other distance. It's not a vector. But we can propose an alternate definition for area. We can say, let the area vector be the magnitude of the area. So we calculate the magnitude of area in the same way as before. But now let also there be a direction, and let that direction be normal to the surface. So if you imagine some surface like the table that you're sitting at, and you imagine a big vector sticking out of it, and that vector is at right angles to the table in every direction. So there's the flat horizontal surface of the table has a vector sticking out of it pointing vertically. Then that is that vector is what we think of as the area vector. So the flux times the area vector, right? If we look at our box here, on this face, okay, let's talk about this face first. On this face, you can see the flux is pointing out in this direction. And then this area here, we can also imagine a vector pointing out of the surface. So here, the area vector and the flux are in the same direction. So that the product of those two vectors is positive. On the other hand, if we look at the surface here, where we have, so this is F and that's E. So this face F, E, D, and so on. This face here has a flux that's entering it, but the area vector here is pointing in the opposite direction, right? Because this is the volume. So the area is pointing out of the volume. So this face has a vector pointing out in this direction, whereas the flux is pointing inwards like this. So here they are in opposite directions. So this, this integral, right, or if you like, this product, dA and F, if this is at the left face, then that will have a negative sign. So this is like saying in minus out, even though we can't see the minus here because it's has to do with the vector, this is effectively flow in and flow out. And in a similar way, if we are looking in the y direction, we have a flow in and a flow out, and in the z direction, flow in and flow out. And so what we see on the surfaces there, that's equal to what we see in terms of the gradients inside of the volume. So that's the divergence theorem that we've applied to our to this box. So then let's put it all together. Let's add together all the changes on all the areas. So when we write it like this, this tells us that it doesn't matter what that volume is like. It doesn't matter what shape we have. We can always take a small piece of that area. So no matter how weirdly it's shaped, right? Let's say we have a weird shape like this. We can draw a little a box here and call that dA. And so we can say here that the total integral on the area is like this. So generally speaking, we can write this. But in our specific case, we have much more regular geometry. So here we have the 6 faces of this rectangle. Excuse me. So we have the 6 faces of this rectangle. So we can instead express this more abstract integral on an arbitrary surface as the sum on these 6 faces here. So basically adding up all these changes is the same as adding up, as integrating across the whole surface. And so if we are doing that, if we are adding together all these area contributions, then we also have to add together all these volume contributions. Excuse me. So we can see we are integrating over the same thing. We are integrating over the volume in each case. And so we can simply add together all these and put them into one integral. And so looking at this, we can see that the integral over the whole area will equal the integral over the whole volume of this the sum of derivatives. And as we mentioned earlier, right, where we were trying to define the divergence of the field, we said it's this gradient in all the directions of the components of the vector. So we can replace all this by the divergence. And then we get the divergence theorem, that the sum of the fluxes on the surface, right, the integral of flux on the areas, that's equal to the volume integral of the divergence. Okay, any questions or comments there? And again, this is nothing but the high dimensional form of the fundamental theorem of calculus, right? So in first year, you met the fundamental theorem. And in this case, you had the line integral of the derivative. And if you look here, that's exactly what we did. So when we wrote this expression, we said that we were looking in one dimension at a time. And so this is, in effect, a line integral, right? These x changes mean we only need to integrate in x here. We are doing it for every single position y and z, but the actual derivative is only in the x direction. So this is effectively the same as the line integral. It's just that we do it multiple times. And so that's why this is virtually the same thing as the fundamental theorem of calculus. It's nothing but the high dimensional equivalent. And by the way, you might think, well, that's now what we can do in 3 dimensions. But of course, we can also use this general view for a 2-dimensional case. So you can think of just integrating on a surface. So if it's a 2-dimensional space, then we regard this volume as that area, and this one would be the line. So if we try and draw it here, in the 2-dimensional case, we would have some area which is bounded by some line, right? So in this case, your volume is actually this interior area here. So if we just do a fill on that. So your blue space there is your is the volume that we are integrating the derivative over, and the red line is in effect the area that we have to integrate over. So we evaluate the divergence. We look at the divergence at the interior points, and we add up across that whole area. And then in this 2-dimensional case, the area is actually this line. And you look at what's happening on the boundaries there. So that's how we can view the divergence theorem in 2 dimensions. So we know how to view it in 1 dimension to begin with, right? That's the 1-dimensional case. It collapses to the fundamental theorem of calculus. We know in 3 dimensions, it's most naturally expressed here, volumes and areas. But what I'm saying now is in 2 dimensions also, we can think of this line, even though it's a 1-dimensional space, we'll call it the area or the boundary more accurately. And then the volume, we'll call that the surface here. So the 2-dimensional case has an analogy with this. And then this theorem, this divergence theorem, it also applies in higher dimensions. So if you think of a 5-dimensional space, a 6-dimensional space, the divergence theorem is also used there. And you'll find in physics something like 22 dimensions sometimes people are trying to work with. So that's the divergence theorem. It's nothing but an analog to the 1-dimensional case. Ahad, you had a question or comment there? Okay, I'm not sure if you're on mute there, but Stuart, you also unmuted there. Question or comment? Everybody good? Just go ahead and unmute and speak if you like. Okay, so that's the divergence theorem. And now we want to apply this to our mass transfer, right? So, and I acknowledge this is pretty abstract, right? But just go back, fundamental theorem of calculus, look at what we're doing here, look for where it looks similar to that, and you're away, okay? And we can talk about it more as much as you like. And of course, we'll be in person on Monday, so that'll be good. But anyway, let's look at now applying this in our material balance case. So of course, in mass transfer, we are interested in a flux. And if we are looking at just the convection flux, we have a velocity and a concentration. And if we want to include diffusion, then we add diffusion terms and so on. But let's just say For now, let's just talk about convection. So if we take that the F, the abstract F that we were talking about earlier, if that's our molar flux, then we can write the same equation. So we said that the rate of change, or let's not think about divergence theorem just yet. Let's think about our just adding up the total number of moles, the rate of change of the moles in our space. So we've got some space, some volume in our system, and we can identify different concentrations at different points in that space. So if we add up the concentration times the volume each time, right? That's a way to read a derivative. If you imagine the finite case, if you take a little box delta V and you multiply it by the concentration, that will give you the number of moles there. And if you add up over the entire volume, then you've added up all the moles in that space. So this is the rate of change of the number of moles in the space. And we can see here that we could expand for the volume. So if this was happening in rectangular coordinates, then we could write this dv as a dx, dy, dz, right? So instead of just one abstract volume variable, we expand that into 3 dimensions, and we then have to integrate over those specific limits, right, for rectangular coordinates. So that's what we've been talking about. And we'll just bring that down here. And then we can imagine that, well, the derivative of this integral over the whole volume, that basically the derivative of the number of moles, we can also get that by taking the differentiation inside of the space. So because the boundaries of the space are fixed, right? We are integrating from A to B and C to D and so on. We don't need to worry about derivatives of the limits. And there are cases where you do have to worry about that. If you look at, there is a formula for this. It's one of the famous names. It's just escaping me at the moment. But there is a formula. It's called someone's formula. Yeah, it's going to bother me the whole day if I don't look it up. But it's anyway, we don't have that problem, right? We've got fixed end conditions here. So we don't have to worry about derivatives of the boundary itself. So we can take this derivative inside of the integral like so. Okay, and if we do that, we have to differentiate concentration with respect to time. But we also have to acknowledge that this concentration is varying in X and Y and Z as well. So we should expand this derivative. We can say, number one, there might be an explicit time derivative in concentration. So we do differentiate concentration with respect to time. Then we can also say the change in that we are talking about here, that could also be expressed due to changes in the X direction. And the way to do that, of course, is by differentiating dc dx and then dx dt. So if we have changes in the X direction of our field, then that will also be observed in this way. And we have to do that for Y and Z also. So once more, if we have an explicit dependence on time, then that will show up here. However, the derivative in time may also show up due to changes in the X direction. So we have to do derivatives like this. And then if we look at these dx dt, dy dt, dz dt, we recognize these are nothing but velocities, right? The rate of change in the X direction, that must be the velocity in the X direction. So we say that's the ux, and similarly uy and uz. So we identify those as velocities. And we can assemble this. We don't need to write these separately like this. We can write it as a vector. We know in maths we have this this nice efficient way of representing things like this as vectors. So we call this a vector. We write it as a column vector. And then looking at what we have, if we look at the equation here, we can see dx, dt, dy, dt, and all of those are multiplied with dc, dx, dc, dy, dc, dz. So we could write dc, dx, dc, dy, dc, dz as a vector. So let's create a vector of the derivatives of c. And then we've got already this velocity vector. So if you look at this, let's say we've written this as a row vector, and we can see u is a column vector, right? So when we wrote u, we wrote it as a row vector that was transposed. That means it's a column vector. So we've got a column vector times a row vector, and it's the dot product, right? So it's not, it's not the scalar. So in this dot product, it's going to be, remember, in your matrix multiplication, you take each element along the row and multiply by each element down the column. So if you do that, you can see that we've got here, this part is the dot product of the vector for the derivative of c and the velocity of the fluid. So we can recognize this then as that kind of product. Okay, so here is a representation as a vector, and so the dot product of these two vectors. And now we also propose another operator. We did propose an operator earlier. We talked about the divergence operator, and that turned out to be a scalar, right? It was the sum of things. But let's define a different operator. So this del operator, so when we say del f, right? Remember, delta is a triangle. This is like an upside down triangle. So delta simply meant the difference between 2 points, whereas del we'll define as the vector of derivatives. So we recognize here we have a del c, right? If we look at this, this is a vector, so we know it's this del type of thing. So it's a vector of derivatives. So we recognize here del c. So in effect, that side of the equation is del c dot producted with the velocity, right? And so that's what we have there. Yeah, so if we go back to our balance here, if we don't have an explicit dependence on time, then we know this is nothing but del c dotted with the velocity, and that's equal to this thing out here. So we now have a way to view this, right? So that's what we have. So that is the same as that. So this is just repeating what we just said, right? This is just going in the opposite direction and saying, if you expand this out, you can see that's what you have. Now what we can also say is that there is a relationship between del and the divergence. I see we are out of time, right? So do spend some time on this, right? I know it's abstract and it looks, it's quite equation heavy and all those things, but each step is quite straightforward, right? It all comes from the fundamental theorem of calculus. There's nothing to remember here. There's no single step that is difficult. In fact, most of these are just integrals and algebra. So each step does follow one from the other. So don't look at this and say, oh, this is beyond me, I'm not even going to try. Do work through each step. And on Monday, we'll continue this, and we'll find, and I'll look for an alternate way to represent this as well. Any questions or comments so far? Okay, if not, then that's it for today. See you Monday.